let's talk about capacitors. That's what we want to do today, right? I don't know, what are we waiting for? So we're moving on to the second half of chapter 19 to talk about a specific object called a capacitor, which helps us to understand how electric fields can be used to kind of be useful. So we're going to talk about capacitors, and then we can shove stuff inside a capacitor called a dielectric. And then we'll talk about what happens if you put capacitors in series and parallel. So we'll learn what those terms mean. Series and parallel is a concept that we will use more often down the road, so pay attention there when we talk about resistors. And then we'll talk about the energy stored in capacitors. Okay, so capacitors and dielectrics. What are these things? A capacitor is a device used to store electric charge. They're used in nearly all electronic devices, so every circuit that you use, your phone, light switches, all sorts of stuff have capacitors in them. Maybe more advanced light switches than a normal on-off switch. What is a capacitor? It's just two pieces of metal separated by a distance. So they're two conductors, but they're not touching each other. There's a small gap in between them. When you connect a battery across them, so that there's a plus side and a minus side, charge is going to build up on either side, and the charge that builds up is equal and opposite. So that's a key thing, equal and opposite. This is a battery, like a car battery, and this is a capacitor, two metal plates separated by some distance. Here's plus charge on this one and minus charge on that one. Okay, that's a typical capacitor. There's another type of capacitor, which is sometimes you'll find them on a circuit board. They're a lot smaller, so how do you make a capacitor with a decent amount of capacitance and then squish it down to fit onto your iPhone circuit? One technique you can do is take like two sheets of aluminum foil, put them next to each other, and then put some plastic in between them, and then roll it up really tightly. So the metal is they're separated and they're tightly wound up to each other, so there's still capacitance there, still plus Q and minus Q separated from each other by this insulator to keep them from being in contact. So these are just two styles of capacitors, a parallel plate capacitor and a capacitor you might find in a circuit. Okay, so the amount of charge, Q, that a capacitor can hold, that's what we care about. That's what a capacitor does, is it separates charge. And the amount of charge separation that a capacitor can do depends on two things, and it's how big your battery is, how much voltage can you apply to the capacitor, so V1 and V2, and then geometrical properties of the capacitor, which is like its physical size. So this is why you wrap this capacitor up in a small shape like that to fit it down to a small area, but you have to make a large physical area of the capacitor itself to have capacitance. So not only is it the voltage, but it's also how much metal there is, basically like its physical size. And we'll talk about how to calculate that soon. So if you have two identical parallel conducting plates, that is called a parallel plate capacitor, okay? And that's what all these things are that we've been talking about here. So you got plus Q and minus Q here, and then remember electric field lines go from the positive charge to a negative charge, and they just go straight over to that. And this is what a parallel plate capacitor is. It's what it does. It creates charge separation, which results in the production of an electric field. So that's why we have capacitors. That's what we want. We want to store charge, and we want to store energy in the electric field so we can use it later. For example, when you take a picture and there's a flash, that energy was built up in a capacitor so you could dump it really quickly out of it. And if you remember, you may or may not remember this, or I don't know how young you are. I'm getting old. Cameras used to have, when you take a picture, you'd have to wait for the flash, and you could hear it charging back up, and that's the capacitor charging back up so that you could take another picture. Okay, so that's what a capacitor does. And even on your iPhone, you try to take a picture, you can't just flash, 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 flash. You have to wait for that capacitor to recharge before you can take another picture. So that's what a capacitor is doing. It's temporarily storing energy in this electric field, separating these charges out, and so on. So since electric field lines begin and end on charges, if there are more charges, then there are more electric field lines, okay? So remember, plus, minus. If you have more plus charges there, more minus charges here, then you're gonna have more electric field lines, and more electric field lines mean a stronger field. So for a parallel plate capacitor, the electric field is simply, if you want to know what the electric field is in this region of the capacitor, it's simply the voltage across it. So if this was a 12-volt battery, then it would be 12 volts. Simply that voltage divided by how far apart the plates are, the D separation. So that's easy. That's it. So this is a special case, is the electric field of a capacitor is just the voltage across the capacitor divided by the distance between it. So the physical characteristics that determine how much charge a capacitor can hold is summarized by one quantity, and it's called the capacitance. So when you buy a capacitor, you don't need to measure its physical properties. You can just look at its advertised capacitance, okay? And the capacitance is this value C, and C relates the charge it can hold to the voltage you apply to it. So if you start applying more and more voltage to it, you get to hold more and more charge. And for 1 volt, how much charge you get depends on the capacitance, okay? And the capacitance depends on its geometry. Okay, so in this equation, this is one of the equations, so you need to know this one. Q is charge, C is capacitance, and V is voltage. C equals Q over V. The unit here, okay, what is charge measured in? Coulombs. What is volts measured in? Volts. What is voltage measured in? Volts. The unit coulomb per volt, or a measurement of capacitance, is farad. The farad is a new unit that you're going to have to get comfortable with, but it's just coulombs per volt. It's named after Michael Faraday, and it's just the unit we use to describe capacitance. All right, the most common capacitance found in circuits, the most common flavor of capacitance or unit or size is the microfarad, or times 10 to the minus 6. So 1 microfarad, that's a mu, Greek letter mu, is equal to 1 times 10 to the minus 6 farads. So that's a really common unit when you build circuits. You'll see that all the time. I need a 20 microfarad capacitor, a 100 microfarad capacitor. Say it with me, microfarad capacitor. It's kind of fun. You should name your kids microfarad. The capacitance, as mentioned, depends on the physical characteristics of the capacitor. So let's say you want to actually calculate what this is. It depends on the total area of the parallel plate and how far apart the plates are. So it's the geometry of your capacitor. It's the area. So if your parallel plate, one of your plates is that size, length times width, that's the area, divided by the distance. So you got 2 of those plates, they're separated by a distance d, then it's just the area of your plates divided by how far apart they are. That's it. And then you get a constant here, which is epsilon naught, and that's just 8.85 times 10 to the minus 12 farads per meter. So epsilon naught never changes, it's a constant, but the area of your plates can change, and so can the separation between them. You can also, instead of having air between your metal plates, you can also fill it with goop, okay? You can fill a parallel plate, instead of with air, you can put plastic or goo or something else. We call that goop a dielectric. So the dielectric is represented by the Greek letter kappa, and it's called the dielectric constant, and it's the property of the dielectric. If you want to change the capacitance of a capacitor, besides changing its cross-sectional area and its how far apart the plates are, you can also put this goop into it, which will change its properties. So you can increase the capacitance of a capacitor by adding a dielectric to it. So you could calculate in this example, they have the capacitance stored in a capacitor, and it's some cross-sectional area divided by a separation there. You get 8.85 nanofarads, so 8.85 times 10 to the minus 9 farads. If you want, you can add a, they don't have an example of that, do they? No, they don't. They don't have an example adding kappa, but if I wanted to, I could add a kappa and change this by some amount, which is found in this table. These different materials have these dielectric constants, kappa, so you can increase. Okay, it looks like I get disconnected there. Wi-Fi. Hopefully that's still good. Okay, I think we're okay. I think we're back. I apologize. That was weird. No. Okay. I think we're back. Okay. All right, let's continue. I think we're good. All right, 19.6. So capacitors in series and parallel. In series, you can hook capacitors up. So you've got one capacitor, another capacitor, another capacitor. So the current, and there's your capacitor here, capacitor there, capacitor here, and this is just the connection to each capacitor. Okay, so capacitor, capacitor, capacitor. You're forcing the current to go through each one. This is an example of that. So you got one capacitor, another capacitor, another capacitor. Now the goal is, what you're going to try and do here is simplify this circuit and do the calculation as if there's only one capacitor there. So the question is, how do you combine these capacitors together in order to create what you need to simplify it down. So in series, the voltage from one side to the other is just the voltage across the first one plus the voltage across the second one plus the voltage across the third one. Okay? And then the total capacitance then, if you want to treat this as one capacitor, is related to the inverse of each one. Okay? So it's a weird equation. So if you want to calculate the total capacitance, you're going to have to do 1 over every capacitance, add them all up, and then do 1 over that at the very end to calculate what it is. So for example, I could say 1 over C total is equal to 1 over 4 farads plus 1 over 2 farads. So I'm going to get, if I do 1 over 4 farads plus 2 over 4 farads, multiply top and bottom by 2 to get a common denominator. 1 over C total is equal to 3 over 4 farads. So then if I want C total, it's going to be 4 over 3 farads. This is 1 over farads. Okay, so then there's my C total. So if I want to add a quarter and a half together, I got to do that first and then flip it upside down to get my total capacitance. That's if they're in series and I want to simplify all these capacitors down into one. If they're in parallel, you see how instead of the current having to go through each of them, it can do separate loops, and that's what it means to be in parallel. So it's like queues at Hy-Vee or something like that, or a grocery store if you don't know what Hy-Vee is. Everybody's in a checkout line and they can serve more than one patron at a time. Same thing, you can have more electrons flowing each time. If you do not do that, if it is in series, okay, you got to go boom, boom, boom. So you got to go through every checkout, like 3 checkouts in a row, which would be weird if that was the grocery store. So in parallel, the voltage at each one is the same. So the voltage, they all start at the same potential, and they each push through with the same amount. So that's one fact you have to know, is that in series the voltage is different at each capacitor. As we would say, the voltage drop is different at each capacitor. And then in the case of in parallel, the voltage drop is the same for each capacitor, and it's constant. So then the total capacitance when they're in series is easy. You just add them all up, C1, C2, C3. It's as if there's just one giant capacitor. It behaves as if there's one giant capacitor. So, you know, if the world is ending and you need to build something that needs a capacitor, I need a certain capacitance capacitor, but you only have 2 or 3 or 4. If you put them together in series and parallel or some sort of combination, you can get the net effect that you need by following these rules and building your radio. Okay, so there we go. So this is the schematic way of drawing capacitors in a circuit. So this would be like your plus and your minus, and then you've got your wires coming in and hooking to capacitors, and these two capacitors are in series, and then this one's by itself. But then if you just combine these together to one capacitor, then these two are now in parallel, and then you can just add them up to get your total capacitance. So you'd have to do, for example, here, if you wanted to combine those, 1 over C total is going to be 1 over 1 microfarad plus 1 over 5 microfarads. Okay, and then that's going to be 5 over 5, so it's going to be 6 over 5 microfarads is equal to 1 over C total, which means C total added together is 6 microfarads, and then you're going to add that 6 microfarads plus 8 microfarads is going to be the total capacitance of this whole circuit if you just simplified it down into one thing. So that's going to be your task, one of the things you will do as a job for this next section and for homework and things, is to simplify circuits to one component from several components. So you have to be able to recognize series and parallel capacitors. All right, energy stored in a capacitor. This is straightforward. The energy stored in a capacitor is just QV over 2. Okay, and then remember that Q is equal to CV, so you can replace that into there, and then you get CV squared. And then again, you can replace the V with Q over C, and you can get this form. So these are all identical forms. Depending on the problem, they could tell you the voltage, or they could tell you the capacitance or the charge. Excuse me, any of those would work, and all of these equations are equivalent. So it just depends on what's your problem. It depends on your problem, whatever your problem is. Okay, that's it. That's all we got. So good luck. See you guys later. Have fun. Ta-ta for now.